What if everything you thought you knew about the universe was just an illusion, a smooth surface hiding a hidden chaos beneath? Picture the fabric of spacetime, the very stage on which planets whirl and galaxies collide. We've always imagined it as a seamless, unbroken expanse stretching endlessly in all directions. But what if, when you zoom in close enough, unimaginably close, that smooth surface shatters into something wild, unpredictable, and utterly strange? This is the quantum foam enigma, one of the most tantalizing mysteries in modern physics. It's the idea that spacetime itself might not be continuous, but instead made up of tiny, frothy bubbles at the smallest scales, like a cosmic ocean churning with unseen energy. Think about that for a second. The ground beneath your feet, the space between stars, even the passage of time, all of it might be built from something granular, something flickering in and out of existence in ways we're only beginning to grasp. This isn't just some abstract theory. It's a radical challenge to this vision of a smooth, geometric universe, crashing headfirst into the bizarre rules of quantum mechanics. And if it's true, it could rewrite the laws of physics as we know them. The implications are staggering. A grainy spacetime could mean hidden dimensions, microscopic black holes popping in and out of existence, or even a whole new layer of reality lurking just beyond our perception. So how do we even begin to unravel such a profound mystery? That's the journey we're about to take together. From the towering ideas of relativity to the mind-bending experiments probing the fabric of reality, we'll explore the cutting-edge science trying to crack this cosmic code. Along the way, you'll meet the brilliant minds daring to ask these questions, the ingenious tools they're using to find answers, and why this search matters not just to physicists, but to anyone who's ever looked up at the night sky and wondered what's really out there. Because if spacetime isn't what we thought, then neither is the universe. Ready to dive in, the idea of quantum foam didn't just appear out of nowhere. It was born from a cosmic collision between two titans of physics. In the mid-20th century, scientists were grappling with an uncomfortable truth. Elegant theory of general relativity, which describes gravity as the curvature of smooth spacetime, refused to play nice with the chaotic, probabilistic rules of quantum mechanics. Enter John Wheeler, a visionary physicist who in 1955 dared to ask, what if spacetime itself isn't smooth at all? He proposed that at unimaginably tiny scales, trillions of times smaller than an atom, the fabric of reality might be a seething, turbulent froth. Picture the surface of a stormy ocean, but instead of waves, you'd see fleeting bubbles of energy appearing and vanishing in a frenzied dance. Wheeler called this quantum foam, and the name stuck because it perfectly captures that sense of constant, chaotic churn. What's fascinating is how Wheeler arrived at this radical idea. He realized that if you combine uncertainty principle, which says particles can pop into existence briefly, with equations for spacetime, you get this bizarre prediction. At the scale, distances and durations become so tiny that spacetime itself might lose its smoothness, warping and twisting like boiling water. Imagine trying to measure the surface of a lake with a ruler made of gelatin. The more you zoom in, the more everything wobbles. That's essentially what quantum foam suggests is happening to reality's building blocks. Today, physicists are still chasing Wheeler's revolutionary idea, but with tools he could barely dream of. Advanced particle colliders, ultra-precise gravitational wave detectors, and even studies of distant cosmic phenomena are all hunting for signs of this spacetime froth. Some theories suggest these microscopic bubbles could create measurable effects, like light from distant stars flickering in strange ways as it travels through the foam. Others propose that if we could peer close enough, we might spot miniature black holes forming and evaporating in the blink of an eye. It's a wild frontier of physics, one that could finally bridge the gap between the vast cosmic scales of relativity and the bizarre quantum realm. And it all started with one physicist's bold imagination, looking at the turbulence of the quantum world and seeing not chaos, but the hidden structure of reality itself. His vision of the universe was breathtaking in its simplicity, a vast cosmic stage where space and time melded into a single smooth fabric, warping gracefully under the weight of stars and galaxies. Picture a trampoline stretching endlessly in all directions, its surface bending where heavy objects rest. That elegant curvature is how general relativity explains gravity, not as a mysterious force, but as the natural shape of spacetime itself. For decades, this idea stood as one of humanity's greatest intellectual triumphs. But then came quantum mechanics, shattering that serene picture with its unruly behavior at the tiniest scales. Take the double-slit experiment, that classic demonstration of quantum weirdness. Fire particles like electrons at a barrier with two narrow openings, and instead of behaving like tidy little bullets, they act like waves, creating an interference pattern as if each particle passes through both slits simultaneously. Even stranger, if you try to measure which slit the electron actually goes through, the interference pattern vanishes. Reality itself seems to change based on whether we're watching. This isn't just a quirk of particles, it's a fundamental truth about the quantum world, where things can exist in multiple states at once until observed. Now here's the cosmic clash. Spacetime is continuous and deterministic, like a perfectly rolled-out sheet of rubber. But the quantum realm is discontinuous, probabilistic, and downright fickle. At the scale of atoms and particles, certainty dissolves into probability clouds and particles wink in and out of existence. So how can these two frameworks, one ruling the cosmos, the other governing the microcosm, possibly describe the same universe? That tension isn't just academic, it's the central puzzle of modern physics. This is where quantum foam enters the stage as a potential peacemaker. If spacetime isn't perfectly smooth, but instead froths with microscopic bubbles at the scale, it might offer a missing link. Those fleeting fluctuations could be the quantum world's fingerprints on pristine fabric, a chaotic undercurrent beneath the apparent calm. Some theories suggest that this foam could subtly alter how light travels across the universe or leave faint imprints in gravitational waves. Others speculate it might even explain why black holes evaporate over time, tying together relativity and quantum mechanics in a single, breathtaking framework. The search for answers isn't just about tidying up equations, it's about rewriting our understanding of reality. Because if spacetime itself has a graininess, then everything from the birth of the cosmos to the nature of black holes might need revisiting. We're standing at the edge of a scientific revolution, peering into the quantum foam's turbulent depths, wondering if the universe's greatest contradiction might also be its most beautiful secret. To grasp just how mind-bendingly small the quantum foam might be, we need to talk about the length, the universe's ultimate limit of smallness. Picture this: if an atom were blown up to the size of our entire solar system, the length would still be smaller than a single grain of sand on Earth. At 1.6 times 10 to the negative 35th meters, it's not just tiny, it's a scale where the very concept of distance might break down entirely. This isn't just a random number plucked from thin air. It's a fundamental boundary woven into the fabric of physics, calculated by combining gravity, quantum mechanics, and the speed of light. Why does this matter? Because below this scale, the violent fluctuations of quantum foam would make spacetime so turbulent that words like here and there lose all meaning. Imagine trying to measure the edge of a soap bubble as it pops. The closer you look, the more the surface churns and dissolves. That's the length's reality, a horizon beyond which spacetime itself might dissolve into a probabilistic haze. Some theories suggest that at this scale, particles and energy flicker so wildly that they create microscopic wormholes or even fleeting black holes, stitching space together in ways we can't yet comprehend. But here's the real kicker: we can't just build a microscope to peer down to this level. The energy required to probe such tiny distances would be so immense that it would collapse into a black hole before we could observe anything. That's why scientists have to get creative, using indirect methods like studying the light from gamma ray bursts billions of light years away. If spacetime is truly foamy at the scale, those high-energy photons might arrive at our telescopes slightly scrambled, their wavelengths jostled by the froth they've traveled through. Other experiments hunt for subtle anomalies in gravitational waves or quantum entanglement, searching for whispers of granularity in the cosmic static. This pursuit isn't just about satisfying curiosity, it's about testing whether our universe has a pixelated underpinning. If spacetime has a smallest possible resolution, it would mean reality isn't just stranger than we imagine, but stranger than we can imagine. Every tool we throw at this problem, from particle colliders to orbiting observatories, is like a blindfolded explorer mapping an unseen landscape by touch, and what they're feeling might just rewrite the rules of existence. The universe is never truly still. Even in what we think of as empty space, there's a hidden frenzy of activity. This is the realm of quantum fluctuations, where energy borrows from nothingness just long enough to conjure particles and antiparticles into existence, only for them to vanish again in a flash. It's like a cosmic game of whack-a-mole, but instead of moles, you have matter and antimatter popping up and annihilating each other in fractions of a second. These fleeting disturbances aren't just quirks of particle physics. They might be the very mechanism that twists spacetime into foam at the smallest scales. Picture a calm pond on a windless day, its surface smooth as glass. Now imagine countless microscopic ripples erupting across it, each one distorting the water's surface for just an instant. That's essentially what quantum fluctuations do to spacetime. When these particle-antiparticle pairs appear, they carry energy, and energy, as showed us, warps spacetime. Multiply this by countless trillions of interactions happening simultaneously across unimaginably tiny distances, and you get a frothy, turbulent sea of geometry. It's not just empty space. It's a dynamic, churning medium where the very fabric of reality is in constant upheaval. One of the most striking pieces of evidence for these quantum shenanigans comes from black holes. Stephen Hawking predicted that near a black hole's event horizon, particle pairs could be torn apart, one swallowed by the black hole, the other escaping as radiation. Over time, this so-called Hawking radiation causes black holes to slowly evaporate. It's a direct demonstration of how quantum fluctuations can have cosmic consequences, warping spacetime so profoundly that even the universe's most voracious monsters aren't immune. Now here's the million-dollar question. If quantum fluctuations can leave fingerprints on black holes, could they also reveal the presence of quantum foam? Scientists think the answer might lie in the behavior of light traveling across the universe. High-energy photons from distant gamma-ray bursts should, in theory, be subtly scrambled if they pass through a frothy spacetime, like a flashlight beam flickering as it shines through turbulent water. Other experiments are hunting for tiny deviations in the polarization of cosmic microwave background radiation, or anomalies in the way entangled particles behave over vast distances. Each of these approaches is like setting up a cosmic microphone, listening for the faint crackle of spacetime's granularity beneath the smooth facade we perceive. The search isn't just about confirming a wild theory, it's about probing the limits of reality itself. If we can catch spacetime in the act of frothing, it would mean the universe isn't just governed by laws, but by a kind of quantum spontaneity, a restless creativity at the heart of existence. And that changes everything. Detecting quantum foam is like trying to photograph a snowflake in a hurricane. The very nature of the phenomenon makes it nearly impossible to observe directly. At the scale where spacetime's supposed granularity churns, the fluctuations are so brief and tiny that they slip through our finest instruments like cosmic ghosts. Imagine building a net to catch bubbles in a boiling pot, but the bubbles vanish before you can even see them. That's the scale we're dealing with. Current technology, for all its sophistication, hits a hard wall here. Even our most powerful particle colliders, like the Large Hadron Collider, can't muster enough energy to probe these infinitesimal distances. To reach the scale, we'd need a collider the size of our galaxy, a machine so unimaginably vast it's practically science fiction. Telescopes face their own hurdles. While they can peer billions of light years across the universe, quantum foam's effects are subtle, like trying to spot a fingerprint on a speeding bullet. Light traveling through frothy spacetime might get jostled, but the distortions would be minuscule, a slight blurring of wavelengths or a delay in arrival time. It's like listening for a whisper in a thunderstorm. That's why scientists turn to cosmic messengers, ultra-high-energy photons from quasars and gamma-ray bursts. These particles racing across the universe for eons could carry faint scars from brushing against spacetime's granularity. If their light arrives with unexpected twists, say, higher-energy photons lagging behind lower-energy ones, it might hint at the foam's turbulence. But here's the catch: the universe is noisy. Cosmic rays, interstellar dust, and other phenomena can mimic these subtle effects. Teasing out quantum foam's signature requires painstaking precision, like isolating a single discordant note in a symphony. Some researchers are turning to gravitational waves, ripples in spacetime itself, which might ripple differently if spacetime has a grainy texture. Others are studying entangled particles, whose spooky connections across space could fray if spacetime isn't as smooth as believed. The hunt is far from hopeless, though. New technologies are pushing boundaries. Atomic interferometers sensitive enough to detect spacetime's faintest tremors, quantum computers simulating scale physics, and next-generation telescopes with unprecedented resolution. Each tool offers a fresh angle on the puzzle, a new way to eavesdrop on the universe's smallest whispers. And while we might never see quantum foam directly, its shadow could appear in the data. A statistical anomaly, a pattern in the chaos, a clue buried in the cosmos's oldest light. What we're really searching for isn't just evidence of foam, but a crack in realities, a glimpse of the universe's hidden blueprint. Gamma-ray bursts are like cosmic fireworks, brief, dazzling eruptions of energy so powerful they outshine entire galaxies in mere seconds. These cataclysmic events, often born from collapsing stars or colliding neutron stars, send shockwaves of high-energy photons racing across the universe. But beyond their spectacle, these bursts might hold the key to unlocking one of physics' greatest puzzles, the granularity of spacetime. Here's how. If spacetime is truly a seething quantum foam at the tiniest scales, it wouldn't be perfectly smooth. It would have microscopic bumps and twists. Photons traveling through this frothy landscape wouldn't glide effortlessly. They'd stumble slightly, like a hiker navigating rocky terrain. The most energetic photons, with their shorter wavelengths, would be more sensitive to these spacetime imperfections. Think of it like driving a sports car versus a monster truck over a potholed road. The low, sturdy truck might roll right over the bumps, while the sports car would feel every jolt. Similarly, high-energy gamma rays should arrive at our telescopes a fraction of a second later than their lower-energy counterparts if spacetime is foamy. This delay, barely perceptible, could be the smoking gun physicists are searching for. Enter the Fermi Gamma-Ray Space Telescope, a cosmic detective launched in 2008 to study these extreme phenomena. Fermi has observed gamma-ray bursts from billions of light-years away, meticulously timing the arrival of their photons. In 2009, it detected a burst from a galaxy over 4 billion light-years distant, and the highest-energy photons arrived within a second of the lower-energy ones. At first glance, that might seem like a blow to quantum foam theories. But the story isn't so simple. Some models suggest the foam's effects could be subtler, or that its structure might vary in ways we haven't yet predicted. The search doesn't end with gamma rays. Other astrophysical messengers are joining the hunt. Neutrinos, those ghostly particles that barely interact with matter, could offer complementary clues. Since they travel vast distances without scattering, any delay in their arrival could point to spacetime's underlying graininess. Even gravitational waves, ripples in spacetime itself, might carry faint imprints of quantum foam as they propagate across the cosmos. Each of these probes is like a different instrument in an orchestra, tuning in to the universe's hidden frequencies. What makes this pursuit so thrilling is its sheer audacity. We're using the universe's most violent explosions as microscopes, leveraging light that's been traveling since before Earth formed to probe the fabric of reality itself. Whether Fermi's findings ultimately confirm or challenge quantum foam, they're pushing the boundaries of what we know, and reminding us that sometimes the universe's deepest secrets are hidden in plain sight, written in the flicker of distant starlight. Gravitational waves are like cosmic messengers, carrying whispers of the universe's most violent events, colliding black holes, merging neutron stars, even the echoes of the Big Bang itself. But buried within these ripples in spacetime might be something even more extraordinary, the faint signature of quantum foam. When LIGO first detected gravitational waves in 2015, it wasn't just a triumph of engineering. It opened a new window into the fabric of reality. These waves stretch and compress spacetime as they pass, and if spacetime isn't perfectly smooth but instead grainy at the smallest scales, that graininess could leave subtle distortions in the signal. Imagine shaking if the sheet were made of fine silk, the ripples would flow smoothly. But if it were woven from coarse burlap, the ripples would scatter slightly, their perfect symmetry disrupted. The key lies in the high-frequency components of gravitational waves. Just as gamma-ray photons might stagger when traveling through quantum foam, the tiniest vibrations in spacetime could be jostled by that same frothy turbulence. Current detectors like LIGO aren't quite sensitive enough to spot these minuscule anomalies. It's like trying to hear a pin drop in a hurricane. But next-generation observatories, like the proposed telescope or the space-based LISA mission, could change the game. With arms stretching millions of kilometers and sensitivity orders of magnitude beyond today's instruments, they might catch the telltale flicker of spacetime's granularity. Some theories suggest quantum foam could imprint a distinctive noise on gravitational waves, a faint crackling in the signal that defies conventional explanations. Others propose that foam-like spacetime might cause gravitational waves to disperse slightly, with different frequencies arriving at slightly different times. These effects would be vanishingly small, but in the precise world of gravitational wave astronomy, even the tiniest deviation could rewrite the rules. The stakes couldn't be higher. If gravitational waves reveal spacetime's hidden graininess, it would mean smooth continuum is just an illusion, a cosmic mirage masking a deeper, wilder truth. We'd be staring at the stitches holding reality together, proof that at its core, the universe is woven from quantum uncertainty. Future detectors might not just listen for collisions in the dark, they could tune in to the static of spacetime itself, hearing the universe's smallest voices for the very first time. While quantum foam paints spacetime as a churning, turbulent sea, another theory offers a radically different vision, one where reality is woven from tiny, indivisible threads. This is loop quantum gravity, or LQG, a bold framework that doesn't just suggest spacetime is granular, but actually calculates its smallest possible pieces. Forget froth, picture the universe as an exquisite tapestry, with each thread representing a fundamental loop of spacetime itself. These loops aren't floating in space, they are space, intertwining to create the very fabric of existence. It's like looking at a knitted sweater under a microscope and realizing the entire garment is made from a single, unbroken strand. Where quantum foam emerges from trying to reconcile general relativity with quantum mechanics, loop quantum gravity takes a more direct approach. It rebuilds spacetime from the ground up using quantum principles. In this theory, areas and volumes come in discrete, tiny packets, no fractions allowed. Just as you can't have half an electron, you can't have half a unit of space. The math reveals a startling prediction. If you could zoom in close enough, you'd see spacetime as a network of these loops, vibrating and evolving in a cosmic dance. It's a universe built not from smooth fabric, but from intricate knots of gravity itself. The parallels with quantum foam are fascinating. Both ideas reject the notion of infinitely divisible space, and both predict wild fluctuations at the tiniest scales. But while quantum foam is chaotic and probabilistic, loop quantum gravity is precise and geometric. One's a stormy ocean, the other's a finely tuned lattice. Remarkably, LQG also offers solutions to some of cosmology's biggest puzzles, like the singularity at the heart of black holes. Instead of infinite density, the theory suggests a quantum bounce, where collapsing matter rebounds into a new universe. It's as if the loops of spacetime act like a safety net, preventing true infinities from forming. Yet for all its elegance, loop quantum gravity isn't the only game in town. String theory, its better-known rival, approaches the granularity question from a completely different angle. Where LQG ties spacetime into loops, string theory imagines it as a vibrating symphony of tiny, one-dimensional strings. The contrast couldn't be starker. One theory weaves, the other plays. But both share a common goal: to reveal whether spacetime's smoothness is just an illusion, hiding a deeper, more intricate truth beneath. String theory takes the quantum foam enigma and spins it into something even stranger. A universe that might not be three-dimensional at all, but a hologram. Picture this: everything you see, from the stars above to the ground beneath your feet, could be a projection from a two-dimensional surface at the edge of reality. It sounds like science fiction, but this holographic principle is one of the most profound ideas in modern physics, and it emerged from string theory's attempt to reconcile quantum mechanics with gravity. The theory suggests that spacetime's apparent three-dimensional volume, along with everything in it, is like a movie screen displaying a three-dimensional image, while the real data is encoded on a flat surface we can't perceive. At the heart of this idea is groundbreaking discovery in 1997, the anti-Sitter conformal field theory correspondence, or AD-SCFT. This mathematical framework showed that a higher dimensional universe with gravity could be perfectly mirrored by a lower dimensional universe without gravity, like a cosmic dictionary translating between two seemingly unrelated languages. Suddenly, the chaotic quantum foam we've been discussing might not just be random turbulence. It could be the pixelated static of this holographic projection, a shadow cast by deeper, more fundamental processes happening at the universe's boundaries. Think of it like a video game. The lush, three-dimensional world you explore on screen isn't stored in your console as a fully rendered landscape. It's generated in real time from lines of two-dimensional code. Similarly, our universe's apparent complexity might emerge from simpler rules written on a distant, two-dimensional surface. If that's true, then quantum foam could be the glitches in the render, the tiny artifacts reminding us that reality isn't as solid as it seems. The philosophical implications are staggering. If spacetime is a hologram, then free will, consciousness, and even our sense of self might be emergent phenomena, dancing on the surface of something far more abstract. It challenges our most basic assumptions about existence, suggesting that the universe isn't just granular. It's an illusion, a breathtakingly detailed mirage. And if that's the case, the quantum foam enigma isn't just a puzzle about spacetime structure. It's a clue that we're living inside a cosmic code, one we're only beginning to crack. Black holes aren't just cosmic vacuum cleaners. They're nature's ultimate quantum foam laboratories, where gravity's crushing grip collides head-on with the subatomic chaos of quantum mechanics. Picture the event horizon, that eerie boundary where light itself can't escape. Here, spacetime isn't just warped. It's stretched to its absolute limits, magnifying any underlying granularity like a cosmic microscope. If quantum foam exists, this is where its effects should scream the loudest. Stephen Hawking's groundbreaking work on black hole radiation hints at why. His calculations showed that black holes aren't entirely black. They slowly leak energy, evaporating over eons. This happens because quantum fluctuations near the event horizon spawn pairs of particles. One falls in, the other escapes, carrying away a tiny piece of the black hole's mass. But here's the twist. This process depends entirely on spacetime's behavior at vanishingly small scales. If spacetime is smooth, the math holds. But if it's frothy, those particle pairs might emerge differently, tangled in ways we're only beginning to understand. This ties directly into the infamous black hole information paradox. If you toss an encyclopedia into a black hole, does its information vanish forever when the black hole evaporates? Quantum mechanics says no, information can't be destroyed. Yet general relativity seems to allow it. Resolving this contradiction might require acknowledging that spacetime itself has structure, like quantum foam's turbulent bubbles storing fragments of that lost data. Some theories suggest the foam's chaotic churn could scramble information, not erase it, like a cosmic blender hiding the ingredients but keeping them intact. Now add quantum entanglement to the mix. When particles become entangled, their fates intertwine across vast distances, defying classical physics. Near a black hole's event horizon, entangled pairs get torn apart, one inside, one outside. If spacetime is granular, this separation might leave detectable imprints, like footprints in the foam. Experiments are already probing this, using black holes as natural amplifiers for quantum gravity's faint signals. The more we study these cosmic extremes, the closer we get to hearing spacetime's hidden whispers, and perhaps finally answering whether reality's fabric is woven from chaos or quantum threads. Quantum entanglement isn't just strange, it's downright spooky. Famously called it or spooky action at a distance, because two entangled particles can instantly influence each other, no matter how far apart they are. But what if this eerie connection isn't magic? What if it's a clue, a cosmic breadcrumb leading us straight to the quantum foam beneath spacetime's smooth surface? Here's the wild idea. Entangled particles might not be communicating through space, but with space, their link woven into the very fabric of reality's granular structure. Picture two corks floating on a stormy sea. From a distance, they seem to move independently. But up close, you see they're connected by the same churning waves beneath them. That's the essence of this hypothesis. The quantum foam's turbulent fluctuations could be the hidden medium that entangles particles, tying their fates together not across space, but within spacetime itself. If true, entanglement wouldn't just defy classical physics, it'd expose spacetime's secret scaffolding. Scientists are already testing this radical notion. In 2017, a team at the University of Vienna fired entangled photons toward telescopes on different islands in the Canaries, separating them by over 140 kilometers. The goal? To see if spacetime's potential graininess disrupts their quantum link. Think of it like sending two synchronized swimmers through choppy water. If the water's turbulence scrambles their rhythm, you'd know the medium isn't smooth. Similarly, if entanglement weakens over vast distances in ways that can't be explained by ordinary interference, it might hint at spacetime's frothy underpinnings. The implications stretch far beyond the lab. If entanglement interacts with quantum foam, it could rewrite our understanding of the early universe. During cosmic inflation, spacetime expanded faster than light, potentially stretching quantum fluctuations into galaxy-spanning wrinkles. Those primordial fluctuations might have left entangled fingerprints in the cosmic microwave background, echoes of a time when the entire universe was a single, quantum-connected entity. Now zoom out further. If spacetime's granularity shapes entanglement, could it also solve the black hole information paradox? Some theories suggest entangled particles near a black hole's edge might encode data in the foam's structure, preserving information even as matter vanishes into the abyss. It's as if the universe keeps a backup copy in the quantum froth against cosmic deletion. The deeper we probe, the more entanglement looks less like a quantum quirk and more like a fundamental feature of reality, a thread stitching together the universe's hidden layers. Whether it's through lab experiments or observations of the distant cosmos, each twisted particle pair could be whispering secrets about the true nature of spacetime. And if we listen closely enough, we might just hear the foam's faint, chaotic hum beneath it all. What if the universe isn't just governed by math? What if it is math? Imagine reality as an unimaginably vast computation, with every star, every atom, even spacetime itself running on a cosmic processor. This isn't just science fiction, it's the bold claim of digital physics, a theory suggesting the universe might literally be a pixelated simulation, built from discrete chunks of information. Think of it like a Minecraft world, where every block represents the smallest possible unit of space and time. But instead of blocks, you'd have quantum foam's frothy bubbles, the universe's raw code flickering in and out of existence. Stephen Wolfram, the mind behind computational universe theory, takes this even further. He proposes that simple computational rules, repeated over and over, could generate all the complexity we see, from galaxies to consciousness. It's like how a handful of basic instructions can create intricate patterns in cellular automata, those grid-based simulations where pixels change state based on their neighbors. Apply that to spacetime, and suddenly quantum foam looks less like chaos and more like the universe's underlying algorithm at work, a cosmic program executing at the scale. The implications are dizzying. If reality is computational, then the laws of physics might just be the universe's operating system. Gravity, just an emergent property of spacetime's data structure. Quantum uncertainty, a glitch in the rendering engine. Even time could be a kind of frame rate, ticking forward in discrete steps too small for us to perceive. This isn't just philosophy, it's a testable hypothesis. Some physicists are hunting for signs of this in high-energy cosmic rays, looking for evidence that particles stutter as they move through spacetime's grid. Others are searching for anomalies in the cosmic microwave background, like a telltale in the universe's oldest light. But here's the real kicker. If the universe is mathematical to its core, it raises a profound question. Is math invented, a human tool, or discovered, a fundamental layer of reality waiting to be uncovered? The quantum foam enigma might hold the answer. If experiments ever confirm spacetime's granularity, it could mean we're not just observers of the cosmos, but participants in a grand computational dance. One where the universe isn't just written in the language of math, but is the language itself. And that would make every one of us, from the atoms in our bodies to the stars overhead, lines of code in the greatest program ever run. Neutrinos are the universe's ultimate ghost particles, so light they barely register as matter, so elusive they can pass through entire planets without a trace. Yet these spectral travelers might hold the key to detecting quantum foam's faint fingerprints. Unlike photons, which interact with electric fields or gravitational waves, which ripple through spacetime's geometry, neutrinos flirt with reality's underlying structure in a unique way. Their oscillations, the mysterious process where they morph between different types as they travel, could be subtly altered if spacetime isn't perfectly smooth but instead frothy at the smallest scales. Imagine a tightrope walker crossing a chasm. If the rope were seamless, their path would be steady. But if the rope had microscopic bumps and kinks, their balance would waver in ways only the most precise instruments could detect. That's the kind of disturbance quantum foam might introduce to neutrinos' interstellar journey. Recent data from experiments like IceCube and SUPER have revealed puzzling anomalies in neutrino behavior. Some neutrinos seem to arrive with energies or oscillation patterns that don't quite match predictions, while conventional explanations, like miscalculations in atmospheric density or neutrino mass, are still in play. A tantalizing possibility remains. These discrepancies could be whispers of spacetime's granularity. If quantum foam exists, neutrinos traversing billions of light years might accumulate tiny deviations, like a ship's course slowly shifting as it navigates a choppy sea. The challenge is isolating these effects from the noise of cosmic rays, magnetic fields, and other interference. That's where next-generation detectors like DUNE, the Deep Underground Neutrino Experiment, come in. DUNE's upcoming liquid argon detectors, buried a mile beneath South Dakota, will catch neutrinos fired from over 800 miles away. With unprecedented precision, it could spot oscillations so slight they'd be invisible to current technology. If spacetime foam is warping these particles' paths, DUNE might catch the statistical fingerprints in the data, a subtle skew in energy distributions or arrival times. But neutrinos aren't the only messengers. Tabletop experiments are also joining the hunt, using quantum sensors so sensitive they can probe spacetime's texture without needing a cosmic source. In labs worldwide, devices like atom interferometers and superconducting qubits are measuring time and space with staggering accuracy. Some theories suggest quantum foam could cause minuscule variations in atomic clocks or disrupt quantum entanglement over short distances. These experiments operate at scales so small they're effectively probing the regime indirectly, like sensing earthquakes through the vibrations of a single grain of sand. Whether through cosmic neutrinos or lab-bound atoms, the goal is the same: to catch spacetime in the act of flickering, revealing the hidden turbulence beneath our smooth, continuous reality. While black holes and gamma-ray bursts offer cosmic-scale tests for quantum foam, some of the most exciting breakthroughs might come from experiments small enough to fit on a lab bench. Imagine trying to measure the roughness of a marble by bouncing laser light off its surface. Now shrink that marble down to the size of an atom, and you've got the essence of tabletop quantum foam detection. Scientists are using devices called atom interferometers, which exploit the wave-like nature of atoms to hunt for spacetime's hidden graininess. Here, how it works: ultra-cold atoms are split into two paths using lasers, then recombined. If spacetime is perfectly smooth, the waves reunite neatly. But if quantum foam introduces even nanometer-scale jitters, the interference pattern should flicker, like a hologram projected onto a vibrating surface. This flickering isn't random noise. It's potential evidence of what physicists call spacetime noise, the statistical turbulence predicted by quantum foam models. The trick is distinguishing this signal from mundane vibrations, air currents, seismic rumbles, even researchers' footsteps. That's why experiments like it operate in vacuum chambers isolated by shock absorbers, listening for whispers of spacetime's fundamental roughness. Surprisingly, these tabletop efforts have drawn interest from the LIGO team, who know a thing or two about measuring spacetime's subtlest tremors. The Nobel-winning gravitational wave hunters have speculated that quantum foam's noise could one day appear in their data as a high-frequency hiss beneath black hole collisions, a static that no amount of engineering can eliminate because it's woven into reality itself. Now enter quantum computers, unlikely allies in this cosmic detective story. Their qubits, exquisitely sensitive to environmental disturbances, might accidentally become quantum foam detectors. In 2021, a Google team noticed unexplained fluctuations in their Sycamore processor's qubits. While most blamed mundane causes, a fringe hypothesis suggested these glitches could reflect spacetime's granularity nudging the quantum states. It's a long shot, but the idea underscores how probing the universe's smallest scales no longer requires just telescopes or particle colliders. Sometimes, the answers hide in the quiet hum of a laser-cooled atom or the fragile coherence of a qubit, waiting for us to decode the universe's tiniest tremors. Quantum computers aren't just revolutionizing cryptography or drug discovery. They might hold the key to simulating the very fabric of spacetime itself. Imagine building a miniature universe inside a machine where qubits don't just crunch numbers but mimic the chaotic dance of quantum foam. This isn't science fiction. It's the cutting edge of physics. IBM and Google have already taken tentative steps into this uncharted territory, using their quantum processors to model how spacetime might behave at the scale. In 2020, Google's Sycamore processor ran a simulation of a holographic universe, inspired by the AD-SCFT correspondence. The results were messy, fragmented, but that's exactly what you'd expect if spacetime is inherently frothy. Here's the radical idea. If we can't directly observe quantum foam in nature, maybe we can recreate its essence in a controlled quantum environment. Think of it like studying turbulence in a wind tunnel, except instead of air, you're simulating the substrate of reality. Quantum computers excel at modeling systems where multiple states exist simultaneously, making them uniquely suited to tackle the probabilistic chaos of spacetime's smallest scales. IBM's quantum team has proposed encoding gravitational interactions as quantum circuits, effectively programming spacetime's geometry into qubits. Early attempts suggest that at these extreme scales, spacetime might not even be a continuous backdrop, but more like a network of interconnected events, buzzing with uncertainty. But the real breakthrough could come from error itself. Quantum computers are notoriously fragile, their qubits prone to decoherence from the slightest disturbance. Yet what if some of that noise isn't a bug but a feature, a glimpse of the quantum foam's turbulence leaking into the simulation? Researchers at the University of Maryland recently argued that certain types of quantum errors mirror the fluctuations predicted by loop quantum gravity. It's as if the machine's imperfections are accidentally revealing the universe's hidden graininess. This work inevitably spills into philosophy. If we can simulate spacetime structure, does that mean reality is, in some sense, computable? Or are we just building elaborate metaphors, like ants constructing a mound that vaguely resembles a skyscraper? The debate echoes centuries-old questions about the nature of existence, now playing out in quantum labs. Some theorists, like Max, argue that if a quantum simulation perfectly replicates spacetime's behavior, it might as well be spacetime, just running on different hardware. Others caution that simulations, no matter how precise, are still approximations, like a pixelated image of the Mona Lisa. The stakes couldn't be higher. If quantum computers can reliably model spacetime's granularity, they might finally bridge the gap between quantum mechanics and gravity, solving equations too complex for classical supercomputers. We could witness virtual black holes evaporate, watch entangled particles warp simulated geometry, or even test whether the universe's laws emerge from something deeper, a cosmic code humming beneath the quantum foam. It's a daring gamble, using machines that barely understand their own quirks to probe the universe's deepest secrets. But if it works, we won't just be studying spacetime. We'll be playing with its building blocks, one qubit at a time. The quantum foam enigma doesn't just rattle the foundations of physics, it shakes the very meaning of reality itself. If spacetime is a seething, probabilistic froth at its core, what does that say about the world we perceive? Take the classic thought experiment once posed to: do you really believe the moon isn't there when nobody looks? It was a jab at the Copenhagen interpretation, which suggests quantum systems only snap into definite states upon observation. Its response: reality isn't about what is, it's about what we measure. Now layer quantum foam into this debate. If spacetime itself fluctuates unpredictably at the smallest scales, can we even trust the stage upon which the moon orbits? The Copenhagen interpretation treats quantum foam's turbulence as inherent noise, a fundamental limit to what we can know. In this view, the foam isn't just a feature, it's a symptom of reality's fuzzy, observer-dependent nature. But not all physicists buy this. Enter pilot wave theory, a controversial alternative that restores determinism by proposing hidden variables guide quantum behavior. Here, quantum foam might not be random chaos, but the visible ripples of deeper, unseen currents. Picture a ship's wake. The churning water seems chaotic, but it's shaped by the vessel's hidden path beneath the surface. Critics of quantum foam argue it's a placeholder for our ignorance, a we don't know yet dressed up in poetic language. They point out that without direct experimental proof, the foam could just be a mathematical artifact, like Ptolemy's epicycles patching gaps in pre-Copernican astronomy. Renormalization in quantum field theory, for instance, sweeps infinities under the rug by assuming spacetime is smooth. If foam exists, why don't these calculations break down? Defenders counter that absence of evidence isn't evidence of absence. We simply lack tools fine enough to probe scale turbulence. The debate spills into metaphysics. If spacetime is granular, does that mean the universe is pixelated like a cosmic video game? Or is it more fluid like an impressionist painting where dots blend into continuity from afar? Some philosophers argue quantum foam blurs the line between ontology and epistemology, between what exists and how we comprehend it. After all, if reality's fabric is fundamentally indeterminate, perhaps existence isn't a binary state but a spectrum of probabilities. Even for all his skepticism might concede one point: quantum foam forces us to confront the limits of language. Words like granular or frothy are metaphors, attempts to map the unimaginable onto human experience. The truth, whatever it is, may lie beyond analogies, waiting for a new formalism, or perhaps a revolution in thought as radical as relativity itself. Until then, the foam remains both a tantalizing clue and a cosmic test, revealing as much about our hunger for understanding as it does about the universe's hidden depths. Not everyone is convinced the universe is built on quantum foam. Some physicists argue it's less a scientific theory and more a captivating metaphor, a placeholder for our ignorance about spacetime's true nature. Nobel laureate Robert Laughlin, for instance, dismisses foam-like turbulence as mathematical hand-waving, pointing out that no experiment has ever directly detected scale fluctuations. Extraordinary claims require extraordinary evidence, he cautions, echoing Carl Sagan. Until we can measure it, quantum foam belongs in the realm of philosophy, not physics. Others take issue with the math itself. Theories predicting spacetime froth often rely on renormalization, a mathematical trick that sweeps infinities under the rug to make equations work. Critics argue this is like balancing a budget by moving debt between columns. If quantum foam were real, they say, these infinities would signal a true breakdown in our models, not just an inconvenience. The late physicist Freeman was especially skeptical, quipping that quantum gravity theories multiply mysteries instead of solving them. But the dissenters aren't just naysayers, they offer compelling alternatives. Take emergent gravity, the idea that spacetime isn't fundamental but arises from deeper quantum interactions, like temperature emerging from atomic motion. This version of this theory suggests gravity is an entropic force, a cosmic side effect of information scrambling at the universe's edges. No foam required. Then there's causal set theory, which replaces smooth spacetime with discrete, interconnected events. Think of a cosmic necklace where each bead represents a moment, connected not by space but by cause and effect. It's granular, yes, but not frothy. Even string theory, often seen as quantum foam's flashier cousin, has splinter factions doubting spacetime's turbulence. Some string theorists propose that what we perceive as foam could actually be holographic pixels, projected from a calmer, lower-dimensional reality, like ripples on a pond masking the still depths below. The debate isn't just academic. Future missions hang in the balance. NASA's proposed ASTRODG would laser map the solar system to precision, hunting for spacetime's hidden graininess in planetary orbits. The ESA's Athena X-ray Observatory, launching in the 2030s, could analyze light from quasars for foam-induced scattering. These projects cost billions. Should we fund them if foam is just speculative poetry? Here's the twist: skepticism fuels progress. Every critic's challenge forces foam proponents to sharpen their theories, design better tests, and confront uncomfortable gaps. Whether spacetime ultimately proves frothy, pixelated, or something stranger still, the real discovery isn't in the answer, it's in the collective struggle to ask the question at all. After all, the universe owes us no clarity, but that won't stop us from looking. The next generation of space telescopes might not just peer deeper into the cosmos, they could glimpse the very texture of spacetime itself. Take NASA's James Space Telescope, already revolutionizing infrared astronomy. While it wasn't designed to hunt for quantum foam, its observations of ancient quasars could inadvertently reveal spacetime's hidden graininess. How? By analyzing the light from these distant behemoths, astronomers might spot subtle distortions, like starlight shimmering through heat waves, that betray the frothy turbulence at the universe's smallest scales. Its unmatched sensitivity to faint, high objects makes it an unlikely but powerful ally in this quantum quest. Then there's LISA, the Laser Interferometer Space Antenna, slated for launch in the 2030s. Unlike ground-based gravitational wave detectors like LIGO, LISA's 3 spacecraft will form a million-kilometer-wide triangle, floating in deep space to catch low-frequency ripples from merging supermassive black holes. These waves, having traveled billions of years, might carry faint imprints of quantum foam's granularity, like a whisper echoing through a cavern, subtly altered by the wall's roughness. LISA's ability to detect frequencies 1,000 times lower than LIGO could unveil spacetime's microscopic structure in ways Earth-bound experiments never could. But why stop there? Visionary physicists are already sketching experiments that sound like science fiction. One proposal involves a scale interferometer, using entangled particles separated by interstellar distances. If quantum foam disrupts their connection in predictable ways, we'd have smoking gun evidence. Another wild idea: harvesting energy from vacuum fluctuations, a concept dubbed quantum froth mining. While still theoretical, these thought experiments stretch the boundaries of what's possible, nudging us toward technologies that might one day make scale physics as routine as particle colliders are today. The burning question isn't just how to probe quantum foam, but when we'll finally crack the mystery. Estimates range from decades to centuries, depending on breakthroughs in quantum computing, materials science, or even serendipitous cosmic discoveries. Some argue definitive answers will require unifying quantum mechanics and gravity into a single framework, a theory of everything. Whether that's string theory, loop quantum gravity, or something entirely unforeseen, the path forward is clear. Keep pushing the limits of observation from the lab bench to the edge of the observable universe. Because if spacetime's secrets are hidden in plain sight, the right tool, or the right mind, might just reveal them when we least expect it. If quantum foam is real, it might be the missing puzzle piece in physics' grandest quest, a theory of everything. For over a century, scientists have struggled to reconcile general relativity, which rules the cosmos, with quantum mechanics, which governs the subatomic world. These frameworks speak different mathematical languages, disagree on fundamental truths, and break down in each other's domains. But what if spacetime's turbulent froth at the scale holds the key to their unification? One promising path is asymptotically safe gravity, a daring approach suggesting that gravity's strength isn't fixed but changes with scale. At everyday sizes, it's weak enough to let you jump without floating away. But zoom into quantum foam's chaotic realm and gravity might become safe, reaching a fixed point where quantum fluctuations balance out, preventing infinite probabilities. Picture a surfer riding an ever-shrinking wave. No matter how small the scale gets, the board stays balanced. If correct, this could mean spacetime's foam isn't random noise but a self-regulating quantum system, with gravity and matter emerging harmoniously from the turbulence. Then there's non-commutative geometry, which reimagines spacetime itself. Instead of smooth coordinates, positions might behave like matrices in quantum mechanics, where measuring x then y gives a different result than y then x. This mathematical twist could turn quantum foam's apparent chaos into an elegant structure, like realizing a scattered handful of dots is actually a constellation. Elaine, the theory's pioneer, argues this approach naturally encodes both quantum weirdness and gravitational curvature, bridging the divide with abstract algebra. The stakes couldn't be higher. A successful theory wouldn't just tidy up equations, it would redefine reality. Imagine explaining black hole singularities, the Big Bang's first moments, or even dark energy through spacetime's granular nature. Practical applications might follow, from quantum computers leveraging foam-like noise to engines manipulating spacetime's fabric. But beyond labs and equations, the cultural impact would be profound. Artists have already drawn inspiration from quantum entanglement spookiness. A validated quantum foam could reshape philosophy, cinema, even music, turning cosmic turbulence into a new metaphor for human creativity. This isn't just physics. It's a reimagining of existence, where the universe's deepest laws emerge from a froth we're only beginning to fathom. Whether through asymptotically safe gravity, non-commutative geometry, or some yet undiscovered framework, the search for unity continues, one scale fluctuation at a time. Hollywood has always had a knack for turning mind-bending physics into blockbuster spectacle, and quantum foam is no exception. Think of Interstellar's breathtaking depiction of Gargantua, the swirling black hole whose warped spacetime mirrored real equations so accurately it spawned scientific papers. But hidden in that cosmic grandeur was a subtler nod to spacetime's potential granularity. Remember the scene where Cooper navigates a fifth-dimensional labyrinth of. That kaleidoscopic structure isn't just visual poetry. It's a pop culture echo of theories suggesting quantum foam could twist reality into higher dimensional threads. Then there's Star Trek, where subspace serves as a handy plot device for faster-than-light travel. While purely fictional, the idea of layered dimensions beneath familiar space weirdly parallels modern hypotheses about spacetime's foamy underbelly. Even Doctor Who's time vortex, with its chaotic fractal swirls, feels like a psychedelic riff on Wheeler's turbulent quantum sea. But here's the catch. Sci-fi often glosses over the messy physics. Warp drives might make for thrilling cinema, but real quantum foam isn't a smooth highway. It's more like a bumpy dirt road at the scale, where folding space would require energy densities that shred matter into subatomic confetti. That hasn't stopped theorists from playing with the possibilities. This famous warp drive concept, beloved by Trek fans, relies on stretching spacetime itself, a feat that might, in theory, exploit quantum foam's fluctuations. Imagine surfing a wave in that churning sea. If you could somehow stabilize the froth's wild oscillations, you might carve a bubble of calm space to ride. Of course, the energy required would dwarf entire stars, and the math is speculative at best. But it's a tantalizing thought experiment, one that blurs the line between sci-fi fantasy and cutting-edge cosmology. For those hungry to dive deeper, the gap between fiction and fact is where things get truly fascinating. Shows like PBS Spacetime and books like Carlos Reality is not what it seems. Unpack these ideas with rigor, separating Hollywood hype from testable science. YouTube channels like even break down quantum foam using everyday analogies, like comparing spacetime's granularity to the of a digital photo, where zooming too close reveals the hidden grid. The takeaway, while we're light years away from Enterprise-style warp cores, the cultural obsession with spacetime's secrets keeps the public hooked on real science. Every black hole rendered in CGI, every wormhole plotted in a screenplay plants seeds of curiosity that bloom in classrooms and labs. And who knows, maybe the next generation of physicists, raised on interstellar and quantum foam theories, will crack the code to make warp drive less fiction and more future. If your curiosity about quantum foam and spacetime's hidden structure has been ignited, there's a wealth of resources to dive deeper. No advanced physics degree required. Start with The Fabric of the Cosmos, in making the universe's most elusive concepts feel tangible. Unravels quantum gravity and spacetime's mysteries with the elegance of a storyteller, weaving in thought experiments that'll make you see reality differently. For a more hands-on approach, the Theoretical Minimum series offers bite-sized, yet rigorous introductions to quantum mechanics and general relativity, building the foundation you'll need to grapple with foam like spacetime. YouTube is another. PBS Spacetime stands out for its deep yet digestible dives into quantum gravity, black holes, and beyond. Host Udaud has a knack for translating equations into vivid analogies, like comparing spacetime's granularity to the static on an old TV screen. For those craving structured learning, platforms like edX host courses from top universities. Quantum Mechanics for Scientists and Engineers, or MIT's String Theory and Holographic Duality, can be challenging but rewarding, especially if you're comfortable with some math. Don't overlook podcasts either. The Joe Experience has hosted physicists like Cox and for wide-ranging chats, while Lex's AI podcast often veers into quantum foundations with guests like Carlo. These conversations humanize the science, revealing how even experts wrestle with spacetime's enigmas. To hear directly from researchers pushing the boundaries, seek out lectures by theorists like Lee or who spent decades probing quantum gravity's frontiers. Many of their talks are freely available online, offering glimpses into the creative chaos of cutting-edge physics. The key is to stay curious, because the day someone finally cracks quantum foam's code, it won't just be in a lab. It might be in a notebook, a classroom, or even a YouTube comment thread where the next big idea sparks. Carlo, the architect of loop quantum gravity, once described spacetime's granularity with poetic simplicity. The world is not a continuum, it's a cascade of tiny, luminous events. In interviews, his eyes light up when explaining how these discrete atoms of space could resolve black hole paradoxes, not with foam, but with woven loops vibrating at the scale. His enthusiasm is contagious, turning abstract math into something almost tactile. We're not just calculating, he insists. We're rediscovering the world as if for the first time. Across the Atlantic, Lee takes a more pragmatic view. On Lex's podcast, he compared quantum foam to the static between radio stations, annoying noise until you realize it's the ambient hum of the universe's quantum processors. His theories flirt with spacetime as an evolving network, where foam-like fluctuations aren't chaos but computational steps in cosmic deep time. Then there's Sabine, whose no-nonsense approach cuts through the hype. In her Frankfurt lab, she tests foam-inspired models with gravitational wave data. If spacetime froths, she warns in a recent lecture, its bubbles would warp light like a funhouse mirror, but LIGO hasn't seen those distortions yet. Her skepticism is a reminder that for all the elegance of theory, nature gets the final vote. Meanwhile, work at the Perimeter Institute takes a radical turn. She envisions spacetime as a quantum graph where foam isn't turbulence but the pixels of reality refreshing, like a cosmic frame rate. Her TED talk on this drew gasps when she quipped, "Your coffee cup doesn't move smoothly, it's teleporting trillions of times per second." These voices share a common thread, awe at the unknown. As muse to The Guardian, the greatest mystery isn't quantum foam, it's why the universe bothers to exist at all. That existential curiosity drives the field forward even as glaring questions remain. Why does foam-like behavior vanish at larger scales? Could it explain dark energy's acceleration? And most hauntingly, if spacetime is granular, what flickers in the gaps between the grains? The answers, if they come, won't just rewrite textbooks. They'll redefine our place in a universe far stranger than we dreamed. For all the tantalizing clues and brilliant theories, quantum foam still guards its deepest secrets fiercely. One of the biggest unanswered questions is whether this frothy turbulence is even observable at all, or if it's forever locked beyond the scale's impenetrable curtain. Imagine trying to hear a whisper from across a roaring stadium. The cosmic static of the universe might simply drown out spacetime's faintest tremors. Yet physicists haven't given up hope. Some speculate that if foam leaves even the slightest fingerprint on light traveling billions of light years, next-generation telescopes could one day catch its blurry signature in the flicker of distant quasars. Others pin their hopes on gravitational waves, where anomalies in the ripples from colliding neutron stars might betray spacetime's hidden graininess. But here, the haunting possibility. What if quantum foam is fundamentally unobservable, not because it doesn't exist, but because the act of measurement itself smooths out the chaos, like a hand steadying trembling water? Then there's the puzzle of black holes, those cosmic paradox machines where quantum foam might play referee in physics' greatest showdown. Hawking radiation suggests black holes slowly evaporate, but where does the information they swallow go? If spacetime is frothy at the event horizon, could those quantum bubbles somehow encode and preserve the data of everything that falls in? It's a wild idea, like suggesting a stormy sea could etch the details of every shipwreck into its foam. Loop quantum gravity offers one provocative answer. Tiny loops of spacetime might knot together at the singularity, preventing infinite density and allowing information to rebound like a cosmic trampoline. But until we can peer inside an actual black hole, these remain breathtaking speculations scribbled on the edge of known physics. Perhaps the most mind-bending question of all is what spacetime even is at the scale. Does quantum foam represent the final layer of reality, or is it just the surface ripples of something even stranger? Hidden dimensions, holographic projections, or a universe built from pure information? Some theories suggest that at these unimaginable scales, words like space and time lose all meaning, replaced by abstract mathematical relationships or a network of quantum entanglement. Picture trying to describe the internet to someone who's only seen a telegraph wire. Our language and intuition might simply fail at the frontier. These aren't just academic riddles, they're invitations. Every unanswered question is a challenge hurled at the next generation of physicists, a cosmic game of hide-and-seek where the stakes are nothing less than reality's true nature. The answers won't come easily. They'll demand new mathematics, wilder experiments, and the courage to question assumptions that even took for granted. But if history teaches us anything, it's that the universe always has deeper layers waiting to be uncovered. The quantum foam enigma isn't a dead end. It's a doorway, and on the other side lies a revolution in how we understand existence itself. From John Wheeler's wild vision of a turbulent, frothy spacetime to today's high-stakes experiments hunting for its ghostly traces, the quest to unravel quantum foam has been anything but ordinary. It's a story that stretches from blackboard scribbles in Princeton to lasers firing across continents, from thought experiments about evaporating black holes to quantum computers simulating the birth of universes. And yet, after decades of searching, spacetime's true texture remains one of science's most tantalizing unsolved puzzles. Is it a seething quantum sea, a pixelated hologram, or something even stranger that defies all our analogies? What makes this mystery so thrilling isn't just the answers we might find, it's how far we've come in asking the question. Wheeler couldn't have imagined LIGO catching gravitational waves or quantum processors mimicking spacetime's birth. Tomorrow's tools, from space-based interferometers to atomic clocks precise enough to detect scale jitters, promise to push the boundaries even further. Each new experiment, whether it confirms foam or contradicts it, peels back another layer of reality's deepest secrets. So where does that leave us? In a universe that refuses to be neatly categorized, where the very stage upon which existence plays out might be as elusive as smoke. Maybe that's the most beautiful lesson of all. The cosmos thrives on paradox, and our attempts to understand it, are as much about embracing the unknown as they are about solving equations. The quantum foam enigma reminds us that wonder isn't just a starting point, it's the fuel that drives discovery forward. As you ponder this, remember, every time you look up at the stars, you're gazing across a space-time fabric that might be shimmering with hidden turbulence. What extraordinary revelations lie ahead? Could the next breakthrough come from a lab, a telescope, or even a comet in a thread like this? The adventure is far from over. Share your wildest theories below, and if you crave more journeys to the edge of physics, hit subscribe. The universe still has countless mysteries waiting, and the next chapter could change everything.